Apologies, everyone. There's some technical difficulties. We'll get started momentarily. All right, sorry about that. I'm presenting from my laptop, which at least previously has been less reliable, so hopefully we don't run into even more technical difficulties than we normally do. But let's see how this goes. Okay, and can you hear me in the back? Great. Then let's not waste any more time. Let's get started. Okay, so today's lecture is about learning linear classifiers. Mostly we're going to talk about gradient descent today. And what's nice about that is it's going to translate pretty nicely into some other kinds of models, more complex models that we're going to learn about later in the course. So we've already seen a few examples at this point of problems that have no analytical solution. For example, things like least absolute deviations, lasso regression, logistic regression. All of these things aren't as simple as least squares linear regression or ridge, where we can just sort of read off the optimal parameters. And as mentioned previously, these problems are typically solved using what we call iterative optimization. And there are a lot of different classes of iterative optimization algorithms that are quite interesting and each have their own pros and cons, so they're good for solving different classes of problems. But we're not really going to cover any of that in this class because what it really is, it's a very large topic of study that's better covered by full classes or even full series of classes like the 127, 227 series. So if you're interested in learning about optimization in all its gory detail, these are great classes to take. But in this class, we're going to mainly stick to gradient descent, which we already introduced last time, and we're going to talk about it in a little bit more detail this time. Oops. Went backwards by accident. Right, so today we're going to talk about gradient descent for logistic regression, and then in the future, we're going to talk about gradient descent for a class of models known as neural networks. And a lot of the same principles that we're going to go over today still apply when we're talking about more complex models like neural nets. And then if we have time today, we started a little bit late, but if we have time, we're also going to discuss in general what it means for something to be a classifier, and then talk from that perspective about a different kind of linear classification learning algorithm known as the perceptron. That's for the end, if we have time. But first, let's quickly recap what we did in the last couple of lectures, just to make sure that we're all in the same place. So specifically, we were mainly looking at logistic regression, right, which represents the probability of class 1. Remember, we were talking about binary classification, right? So the probability, the predicted probability of class 1 is represented as this function known as the sigmoid applied to the output of my model, right? And specifically, my model here was linear. So f theta of x is just theta transpose x, right? And then I pass that through a sigmoid, which squashes the number to be between 0 and 1, and that gives me my predicted probability of class 1. And then similarly, I could define the probability of clause 0 just to be 1 minus that. And here's what the sigmoid looked like. And then last time, you'll remember, we also worked out that for maximum likelihood estimation, right, the gradient took this particular form, right, x transpose times y minus s theta, where s theta is some vector that contains all of these sigmoid values, right? This is what we saw last time. We computed the gradient, but then we saw that it's not so easy to just say, well, let's actually set this gradient equal to 0 and solve for theta. There's not really anything like that we're going to be able to do for this particular problem, right? We can sort of characterize what the solution looks like if the gradient equals 0. And remember, we actually said that maybe it's actually not so great because we have these theta entries that are growing in magnitude unboundedly, right? Nevertheless, even just trying to set this gradient equal to 0 is not going to produce anything of value because we just don't know how to take that and then solve for theta. So then instead, what we end up doing, am I still here? What we end up doing is what we know is what's known as gradient-based optimization. We're back. And for the easy problems that we saw previously, right, we would just set the gradient equal to 0 and then read off what the parameters were that we wanted them to be. And that doesn't work here. We can't just set this gradient equal to 0 and solve for theta. If you manage to do so, again, let me know. But I don't think anyone's going to be able to actually successfully do that. So instead, in this gradient-based optimization, iterative optimization scheme, what we're going to do is we're going to try and follow the gradient. Is this slide going to? Oh, there we go. OK, so we're going to try and follow the gradient. What does that actually mean? Well, at a high level, basically what it means is we're using this gradient information, OK, to iteratively update our parameters theta over and over and over again in order to try to push ourselves into a set of parameters that satisfy that the gradient is equal to 0. And once we get there, hopefully that means that we've found our optimizer. We found our minimum. There's some other, checks that we should do in order to make sure that that's actually the case. But this is the general flavor of gradient-based optimization, using gradient information to iteratively update our parameters until we reach, some optimum. If I do this for maximization problems, like MLE, then we call this gradient ascent, because basically we're moving upwards in order to try and find a maximum. But for the most part, in terms of machine learning, when we're doing minimizations, like minimizing a loss function, that's typically how we characterize things, right? This is gradient descent, where I'm moving downwards in order to try and find a minimum, right? And these two things are essentially equal, except for a negative sign in one of them, right? Maximum likelihood estimation is the same thing as minimizing my negative log likelihood. So, all of it is, the same. It's just, what sign you choose to use. But gradient descent is usually how we think about problems in machine learning. So let's actually pause for a second and think about what does it mean? What does it actually mean to follow the gradient, quote unquote? Well, what we're doing here, right, is we're trying to find parameters that minimize, this, average over my data set of the loss values, right? We're trying to find parameters that minimize that. For example, this could be like the negative log likelihood loss, which corresponds to MLE, right? All I'm doing here is I'm also dividing by n, right, to make things an average instead of a sum. Sometimes that just makes things a little bit nicer, but it doesn't actually change the optimization problem itself, right? What gradient descent is going to do is it's going to move my parameters theta in the direction of the negative gradient of my average loss, okay? So remember, we saw something like this last time, right, where we have our loss, and then we take an average over the entire data set of that loss, and then we compute the gradient with respect to my parameters of that average loss. And then here I have some alpha, which I call, a learning rate or a step size, and I move my parameters theta in the negative direction of that gradient by some small amount alpha, and then I set that to be my new parameter. So this left arrow, remember, is like an assignment, right? I do everything on the right side, move my parameters in a small step in the direction of the negative gradient, and then set that to be equal to my new parameters, which again I call theta, because I call everything theta, and alpha is some small number. Think of it on the order of like 0.01, 0.001. Or actually, it kind of depends on the problem that you're working on, but it's generally in that range. We call it a learning rate or a step size. And here's a not obvious statement. Okay, so I wrote it, and then I'm not going to prove it because we don't have time to do so. But it's good to know. But don't think, oh, I don't know why this is the case. That's okay, because we're not actually proving it, and it's not obvious. For well-conditioned problems and small enough step sizes alpha, we will eventually reach some parameters theta if we keep doing these gradient updates over and over and over again. We will eventually reach some parameters theta such that the gradient with respect to those parameters is 0. In other words, hopefully we found a minimum, right? But we found something that we call a critical point, where the gradients are where the gradient is equal to 0. I think I saw a question up there.
Yeah, sorry. I see that that's the gradient symbol in respect to theta, but is that of the average loss function?
Right. Okay. So this whole thing over here, right? So this is the gradient with respect to this entire thing. Yeah, the gradient with respect to the average loss. Yeah. Yes. Oh, sorry. Okay, yeah, no, that's okay. You and then up here in the front. Yeah. So you can go first. Oh, yeah. You had a question, right?
Oh, me?
Yeah.
Okay, yes. Sorry.
No worries.
Could you maybe draw out a demo of
I'll do that on the next slide.
Oh, okay.
Yep. Actually, I'll do that on both the next slide and the next slide. Yeah.
Does it matter if we, is there a reason why we're minimizing the average loss? Does it matter if we, have 1 over n?
Yeah, right. So does the 1 over n actually matter? Not in terms of the optimization problem itself. Like the minimizer of the average loss is the same as the minimizer of the summed loss. Usually we work with average because it leads to a slightly easier optimization problem. And there's nothing at that point that actually depends on the size of your data set. You know what I mean? Like the summed loss grows as my data set grows, which is kind of weird, right? Like if I had like 1 million data points, then the summed loss would just be huge. And then we won't go into this in detail, but that actually makes optimization harder. I might have to choose like a much smaller learning rate in order to compensate for the fact that my losses are huge. So just working with average loss just takes away annoying factors like that, so I don't have to think about it. Okay, so let's actually draw some intuition for what gradient descent would look like if I was working in 1D. Normally I draw using a reference, right? Like there's something else that I have open. I have technical difficulties today, so I'm drawing from memory. But I think I know what this is supposed to look like. So, in a 1D problem, right, I have a single dimension of my parameter theta, right? So it's like one number that I'm optimizing, right? That would never actually be the case. This is just for visualization purposes. And then I can, draw the loss with respect to those parameters on the y-axis, on the vertical axis, right? So let's say that my loss function, for example, looks like this. So there's like some setting of my loss that's going to minimize it, somewhere in this range over here. And then as it, moves away from there, it kind of looks like it's, the loss is getting worse quadratically. Like those are bad parameters, right? So let's say that, at some current step in my optimization, I'm here, okay? So this corresponds to, my parameters being this particular value on the horizontal axis, right? So I compute my loss, I compute my gradient, or in 1D, it's just a derivative, right? That makes things easy. What is a derivative? Well, a derivative is the slope of this tangent line to the function at that point, right? So it's the slope of this blue line right here. Well, what is the slope? Don't exactly know because we didn't draw units on these, right? But we can see that the slope is negative, right? Which means that at this point I would have a negative derivative. If I'm doing gradient descent, where I move in the negative direction of the gradient or the negative direction of the derivative, and my derivative is negative, that means I'm moving in the positive direction, right? Negative, negative, right? So that means I move theta in the positive direction. So I'm moving theta this way, right? In the positive direction, I might end up somewhere like here, depending on what my alpha, what my step size is, right? And maybe I'll end up like somewhere like this. And we can see indeed that we've actually accomplished our goal. We've actually made the loss smaller, right? If this was my gradient step, I'd be pretty happy about this because I started from some theta which was worse in terms of the loss, and I got to some theta which is better, right? We can see that this is not always a great idea. For example, like if I have an alpha that's too large, right? What could I do? Well, I could like totally overshoot this entire area and then wind up on the other side, maybe even with a loss value that's bigger, right? Certainly I want to do something like that. And so careful setting of a small step size alpha turns out to be a very important piece of the puzzle in order to get things like gradient descent to actually behave well. Yes? Oh, great question. So is alpha a constant over the course of training, or can it vary? It can vary. Sometimes people use what are known as like learning rate schedules, such that the alpha maybe like gets smaller as you train for longer. This is a topic that we will touch on a little bit later on in the course, but it's not really ever going to be the focus of what we discuss. Yeah. For simple problems like logistic regression, it's not usually that important. We usually just use a small constant step size. We can also analyze the other side of this. So like, for example, what if I'm over here? What's my derivative? Right? It's the slope of this tangent line, and the slope is positive, right? So if I'm in the positive derivative, then I move theta, right? I'm moving theta in the negative gradient or the negative derivative, right? Which for a positive derivative would be in the negative direction, right? So if I'm here, in terms of theta, I'm moving this way, right? So maybe I end up somewhere like here. And as you can see, we've again succeeded, right, in finding a new theta that is better at minimizing our loss function. Yes?
Does the actual value of the derivative matter, or is it just if it's positive or negative?
Does the value of the derivative matter? Yes, it does, right? Because the value of the derivative determines essentially, like the magnitude of how far it is that you're trying to go. That times alpha is going to tell you how far to go. So actually, I didn't really draw it, but here, my derivative in terms of magnitude is larger than here, right? So what I probably should have drawn is that like this blue step would actually be bigger than this orange step over here. Lastly, if I'm, for example, somewhere like here, right? Well, drawing errors aside, the slope of my derivative is 0, right? If I have 0 derivative, then I don't move. Okay, and that's good because maybe that's like a minimum. I don't want to move away from the minimum, that's for sure. So then that's where I stop. Yes? Yeah, great question. So 0 derivative does not necessarily mean for all functions, right, that I've found the minimum or the global minimum, right, like the thing that globally minimizes my loss function. I could have all sorts of different functions. It could look like this, so there's 0 derivative, but it actually can keep going, right? Or in higher dimensions, I have these things called like saddle points and all these weird artifacts of the landscape that might make things hard. In general, for those types of functions, gradient descent has no guarantees that you won't get stuck there, that you won't get stuck at a saddle point or a local minimum or things along those lines. And there are kind of different ways that you can deal with these types of problems, like tweaks to your optimization or just better techniques in general. Logistic regression has a very nice property called convexity. And also, if you have logistic regression plus L2 regularization, then you have something called strict convexity, which basically says that no matter where I initialize theta from, I'm going to get to the global optimum. Logistic regression is a very nice problem like that. When we get to more complex models like neural networks, we're going to throw all of that out the window because it turns out, practically speaking, we don't care that much. But theoretically, logistic regression is very nice in this way. Okay, I want to give you one more visualization, which is in 2D. Now in 2D, I would really want to draw a three-dimensional thing, but I can't, right? So instead what we do is we draw these isocontours, these level sets, right? So imagine that these level sets represent, a loss function which kind of looks like a bowl, right? And then as I move away from the center of that bowl, my loss is getting worse and worse, maybe like quadratically or something like that, right? So then I have two parameters, theta 1, right, and theta 2. And then I'm asking basically, what would gradient descent look like for a problem like this? Well, here's what I'm saying is the optimum, right? That's the set of parameters that I really want to find, right? And I'm hoping that gradient descent, regardless of where I initialize it, will hopefully find me that thing. So let's say, for example, I start here, okay? And then I ask, well, where is gradient descent going to take me? Well, there's a bit of a different geometric picture here because this is visualizing isocontours, level sets, right? It's no longer visualizing the function itself. And so I claim I'm not going to, try to prove this, but the gradient is actually perpendicular to the tangent line intersecting at one point that isocontour that I'm on. So the gradient is actually going to point in this direction, over here. Drawing errors aside, right? But I have an isocontour, I draw a tangent to that isocontour, my gradient points in the perpendicular direction to that tangent that I just drew, okay? And, depending on what my alpha is, it's a little hard, to say, but, let's say that, for example, I pick an alpha that's kind of large, just for, think just as a thought exercise. If I pick an alpha that's kind of large, well, when I'm out here, I'm actually pretty far away from the minimum. So if this is something that looks quadratic, my gradient's going to be big in terms of magnitude. And so maybe my step size is going to carry me too far. Maybe it carries me all the way like over here or something like that. And if that happens, then here's the new point that I arrive at, right? And then what do? Well, I do this gradient descent procedure over again, right? So I draw this tangent line, and then I move perpendicular to that tangent line. Now, my loss value is smaller, right? I'm in an isocontour that's closer to the minimum. Therefore, my gradient's also going to be smaller. So even with the same alpha, I'm going to move with smaller compared to the first step that I took. So maybe this time I only get here. And then rinse and repeat. You can move back in this direction. I think the scales that I've drawn here are actually kind of off. Try to ignore those. This is just for visualization, right? And then we'll move in this direction. Ad infinitum, ad nauseum until we get to the optimum or we get really impatient, right? So here, one funny thing that you can actually see that's kind of going on is that gradient descent is actually not making, very efficient progress towards the optimum. It's kind of doing this ping-ponging thing, right, where it's oscillating back and forth, and it's making some progress every time, but it looks like it's actually, taking a lot of wasted effort in order to try to get there. Gradient descent is kind of suboptimal in these ways, and there are various, techniques, optimization techniques that can be used to sort of correct for this. Not something that we're going to talk about a lot in this class, but it is good to know that, gradient descent is the basic, and then we can add on top of that in order to make things better. Yeah.
Let's say maybe you know something about this distribution and the size that you move in one direction is different from the other one. In that case, would you still move perpendicular to the gradient, or would you be slightly off?
Yeah, great question. So if I knew something about, let's say, the curvature, for example, of this loss landscape, then I can do better things than gradient descent. For example, if anyone's ever heard of Newton's method, it's a method that uses not just gradient information, but also second-order Hessian information, right, which kind of tries to correct for quadratically speaking, tries to correct for the curvature that you're actually working with, so that maybe instead of, following something like this, I instead just go directly in the direction that my optimum would be. So actually, for quadratics, right, Newton's method is optimal in the sense that it can get you to the optimum in one step. Nevertheless, that is not necessarily always going to be the case for more complicated loss functions. Approximations always have to be made, and there are always these trade-offs. Like Newton's method can be a lot more expensive because we're trying to not just compute the gradient but also the Hessian, which is this big matrix a lot of the times, right? So there are various ways to try to either correct for curvature, or other people try to think about like adapting the step size in every direction differently, so that maybe you move more along theta 2 than you do for theta 1. And then sometimes that can result in better updates as well. And all of those are kind of a little bit outside of the scope of this class. We'll stick to gradient descent for the most part. Yeah? Is this guaranteed to converge if alpha is too big? No. So there are certain bounds, like if you decay alpha proportional to, or inversely proportional to like the square of the number of iterations you've taken so far, then you have like guarantees on like how close you'll get to the optimum and things like that. All of those bounds are relatively complicated, but usually, or basically never, is it the case that you can just use whatever alpha you want and you'll actually still converge. You need one that's small enough, and oftentimes one that's decaying as well. Okay, great. Let's actually talk a little bit now about what gradient descent looks like for logistic regression. So we've talked about gradient descent in general. We've also tried to visualize a little bit of what it's actually doing. How does it apply back to all the logistic regression stuff we had before? Well, it's pretty simple, right? So for logistic regression, we start from some parameters theta, and we perform this gradient update. All I've done here, right, is I've substituted in the gradient of the average loss with this gradient that we already computed, right? With one small difference. Before we had y minus s theta, now I have s theta minus y. Why? Because I negated the maximization that we were doing before, right? Now we're doing a minimization, so I swapped those two terms just to make it the minimization that I'm looking for, okay? And then I might also want something like a 1 over n in front of this whole term. But just for notational convenience, I'm going to leave that out and pretend that I divided my alpha by n already in order to make things work out properly. We can actually take a look a little bit at what this update is actually doing. So remember, what is my y? My y is this vector that contains zeros and ones. That's all it contains, right? And then my s theta contains values that are all between 0 and 1, okay? What does that mean? It means that when y is 0, okay, for all my negative examples, this whole value here is positive, right? And then when y is 1, right, for all my positive examples, this whole thing is negative, right, because s theta is between 0 and 1. So s theta minus 1 would be negative. And then all I'm doing with these positive and negative values is I'm sort of multiplying them by the respective data points, right, all of these xi's, and then moving theta with respect to all of these data points that I have. So basically what's actually going on is that theta, you can think of it as moving towards, quote unquote, all of my positive x's, or all of my x's that correspond to positive classes, right, the positive class, and it's, quote unquote, moving away from all of the other x's which have the negative label, okay? So we can almost think of like, negative examples, positive examples, and then my theta is trying to become more like the positive x's and becoming less like the negative x's. It's a good exercise to try to think about why this makes sense in the context of what the logistic regression model is. And I'm going to leave this as an exercise, but just think about the parameterization of the model, what it's predicting, and why it would make sense to update theta in this way. But another good thing to note is that the more wrong that my s theta is, the bigger move I'm going to either make away or towards that particular xi, right? Because if the predicted probability is close to 0, and then y for that was 1, then I'm going to have a bigger negative value than if I had predicted something close to 1 instead, right? So the magnitude with which I care about all of these different xi's corresponds to how wrong, how incorrect my model currently is about that particular data point. There's actually a little bit of a problem here. So I put moving towards and a moving away in quotes because it's not actually really doing that. We're not really actually moving towards or away from the x's in particular. What we're doing is we're actually repeatedly adding to our parameters theta, right? We're repeatedly adding these x values over and over and over again. And because of that, our magnitude of theta grows unboundedly. This is already the problem that we talked about before, right? The magnitude of theta goes to infinity, essentially, as I take more and more gradient steps, as my number of steps goes to infinity. Right, and so what's the fix here? Well, hopefully you already know. If you're not sure, go back and review the last lecture, see what we talked about there, and make sure that you understand what the way to fix this is actually going to be. Okay, let's talk a little bit now about stochastic optimization. Some people refer to what I'm about to say as stochastic gradient descent, or SGD. SGD is an abbreviation that you're going to hear all the time. So it's good to know that this is what they're referring to. It's a little bit of a misnomer, but for reasons that are relatively unimportant. So we're going to call it stochastic gradient descent, or the stochastic gradient method, or whatever. Just know that this is what I'm talking about. The basic idea or the motivation behind stochastic gradient descent is that computing this gradient of the average loss can be really expensive if I have a lot of data, if n is really, really big, right? Like, today in machine learning, it's not uncommon for n to be like 1 million, right? And so taking the sum of losses over 1 million data points can be extremely expensive, and we don't actually necessarily want to do that every time we just want to make a little update to our parameters, right? Gradient descent is making a little update to our parameters based on the step size alpha, and to do that huge amount of work just for this little update seems like it's totally not worth it, right? It's going to take forever in order to try to make progress this way. So instead, in stochastic optimization, what we end up doing is we pick a smaller number b. B is much less than n. That's what these two arrows mean. Okay, some number that's much smaller than n typically. And we call that b our batch size or our mini batch size. And then what we do is we compute our gradient of our average loss with respect to only b data points rather than all of the data that we have. Okay? And if we sample these data points, these b data points, IID from our training set, then we still get a pretty good estimate of what the average loss is. So as b gets larger and larger, and as long as we do this sampling IID, then we're going to have, essentially this gradient is going to be, remember what we talked about in lecture 2, this gradient is going to be a Monte Carlo estimate, a Monte Carlo approximation of the real gradient that we want, right? So if b is large enough, doesn't even have to be that big, think like, 32 or something like that. As long as b is large enough, and we sample our data IID, then we're still going to have a pretty good estimate of the gradient that we want, but at a fraction of the cost, right? So that's the important part, is we're taking all of these gradient updates, we want all of them to be fast, and to do so, we need to pick a b that's much smaller than n if our n is really large. For a problem like logistic regression, we can actually even consider b as small as 1. It's not that uncommon to see something like that. And this is actually, theoretically speaking, what a lot of people think about when they say stochastic optimization, is literally picking one data point at a time. And what this would look like is you randomly select some point from your training set, xi, yi, for some random I, and then you update your parameters according to the gradient, but just with respect to that one data point, right? And then that one data point ends up looking, the gradient for that one data point ends up looking like this, right? Where this is our s theta, but now just one number. This was our y, right? And then this is our x. So same thing like we had before, just we can do this one data point at a time if we really wanted to. And sometimes this is a better trade-off in terms of how fast we can converge to our optimal theta. Okay, so because each one of these is going to be really, really fast, which means we can take way more steps a lot more quickly. And doing so is oftentimes better than computing a really accurate estimate of our gradient. If we're only going to use that to take some tiny little step, then doing all that work just wasn't worth it to begin with. That's the motivation behind stochastic optimization. Yes?
Would it matter how the sampling is done for the batch size? Is that any importance at all?
Would it matter how the sampling is done for the batch size?
Maybe like a uniform versus something else?
Right. So the way that each one of these xy's is sampled, is that the question, by the way? Yeah. Yeah, that's just like uniformly pick at random some point from your training set, and then repeat that process b times. So it's like an IID sample for my training set, like uniformly over the entire training set. And doing things other than that, it essentially just makes this Monte Carlo approximation worse. There are good reasons why you might want that for particular applications, but in general, we're always talking about uniformly sampling from the whole training set. Yeah, yes?
Are we going to draw out like a batch size demo?
Are we going to draw out a batch size demo? So I'm not sure exactly what that means. Do you mean like how?
Just like walking through, just like we were before, like for every step, but just, I don't know, maybe like, I'm having maybe a little bit of a tough time visualizing what the batch size does.
What does the batch size do?
Just what the batch does.
Oh, here's my whole training set, right? And like, I have like n different training points, right? Where like, n could be very, very large, right? All I'm doing when I say I pick a batch size b is that for, this entire thing, I'm going to randomly sample b. You can think of them as like indices, right? Uniformly from 1 to n, right? And then for every index that I sample, I just grab the corresponding data point and I pull it out, and I do that b times, right? Until I form a batch of b that's like much smaller than the n that I had before, right? And then using that, I do everything the exact same way I did before, right? Compute the gradients and all that other kind of stuff. Yeah. Yes.
I have two questions. The first one, you mentioned that like if we could pick a batch size like of 1 or like small, right? We could run a lot of iterations, which is like intuitively makes sense to me. But that makes me think if we're like going from in order, right? Like by the end, the weights aren't really going to be suited for maybe the first one. So it kind of reminds me of like Delta and Forest from CS170.
Interesting.
If you go back until nothing changes again, is it similar to that where you have to, like you mentioned like you can iterate a bunch and even bound about n or just like can it go through again and again until
Good question. So there's two answers that are both important. The first one is that practically, yes, we do oftentimes make multiple passes through our data set. So it's, and each one of these we usually call an epoch, E-P-O-C-H, right? And we might do like 10 epochs or like 200 epochs or whatever. That's like how many times do I see each data point, right? On average. The second part of the answer that I think is important is that in general, I'm not talking about it on this slide, right? But in general, we are actually introducing errors, right? Errors in terms of the gradient computation. It's now like an approximate computation of the gradient that I want, right? Whereas before, my gradient computation with respect to my training set was exact. Now there are errors involved, and those can lead my parameters, theta, into regions that don't necessarily actually minimize the loss, right? And so, for example, I could do that if I have, certain data points, and then later on, I have data points that like, maybe I forgot about in terms of like, the theta is no longer suited for that. And so that error is kind of hard to, it's kind of hard to analyze. But if we're doing this, sort of like IID sampling, usually we can sort of analyze it in such a way that it kind of goes away. And, it still makes sense to do this just from a computational perspective, as long as we make enough passes through our data set so that we can be sure that, the parameters are suited for basically all of our data.
And then the second question I have is, like, you kind of moved into the slide with, I think, the intention of kind of saying, like, okay, theta might go to infinity, so how do we fix that, right?
Oh, sorry, that was unrelated. Yeah, so theta might go to infinity. How do we fix that? I didn't answer it because I feel like I've, addressed it a couple of times in lecture already. That's just something for you to think about yourself. Yes, that is the correct answer. Yeah.
How would that fit into the update argument, or is it like within the loss function?
So that's not actually on this slide, but it's an extra term in your loss, right? So then you have to compute the gradient with that term, with respect to that term as well. Yeah. Hmm? Now I'm switching gears again, okay, and we're going to zoom out and actually talk about classifiers. Believe it or not, we actually haven't really talked about classifiers yet. You might be wondering, what does that even mean? Well, here's what I mean. Really pedantically speaking, okay, statisticians will say this to you sometimes, a classifier is technically two things. It's a combination of a model and a decision rule, okay? So we've talked about models so far. We've actually not really talked yet about decision rules. We actually kind of glossed over it when I talked about LDA, linear discriminant analysis, but other than that, we actually haven't really talked that much about decision rules. So we've talked about models. For example, my model could be probabilistic, right? It could be like logistic regression. That's an example of a model, right? But then what I have to do is I have to pair that model with something that actually tells me, should I predict 0 or should I predict 1? Something that's actually making that decision, right? That's why we call it a decision rule. And it really doesn't have to be complicated, right? Like think of like, the very intuitive decision rules are probably the ones that are going to be the most sensible. For example, for a probabilistic model, my decision rule can be predict the class that has the highest predicted probability, right? Now, there are variants on this that I might actually consider, but in general, we can think of things that are as simple as this, and they usually make sense, right? Pair my logistic regression model with a decision rule that says whichever predicted probability was higher, 0 versus 1, predict the corresponding class. Okay, this is just to be pedantic, but it is good to know that this is, technically how people think about classifiers. If I choose this decision rule, predict the class that has the highest predicted probability, then for logistic regression, this actually turns out to have a really nice simplification. And it's as follows. We predict class 1, right, if that's more likely than class 0. When is it more likely? It's more likely when the predicted probability is greater than 0.5, because that means that the other probability is less than 0.5, right? And for exactly 0.5, 0.5, then, doesn't really matter. We can just pick one of them. But when is the predicted probability of class 1 greater than 0.5? Well, it's when the sigmoid of my model output is greater than 0.5, because that's how this probability is defined in the first place. When is sigmoid of theta transpose x greater than 0.5? Does anybody remember that graph and can tell me when that sigmoid is going to be greater than 0.5? Yes. Yes, right? So it's greater than 0.5 when the thing on the inside, right, theta transpose x, is greater than 0, right? So if I have a theta transpose x that's positive, that means that my predicted probability of class 1 is going to be greater than 0.5, which means that my decision rule would pick that class, right? On the other hand, if theta transpose x is negative, then the predicted probability of class 1 is less than 0.5, so my decision rule would pick 0, right? So basically what we're saying here is that for something like logistic regression, all we actually really have to do is look at the sign of the model output in order to perform classification. So I was doing all this business with like, take the model output, put it through a sigmoid, that's my probability, yada, yada, yada. That's all good, it's good to know what the model is, but if I only want a decision, if I only want 0 or 1 for a particular x, I can actually skip all of that business at the end. I can just look at my model output directly, theta transpose x, look at the sign, and then make a decision based off of that, right? I can skip the whole sigmoid business, right? So it's kind of a shortcut when we're looking at logistic regression is that this is what our decision rule is, and it corresponds to a nice simplification of what the model actually is. And as it turns out, it's going to be often the case that for many of the models that we work with, there are similar simplifications where we don't have to run the full model, right, in order to figure out what probability or what class we should predict. There's going to be some shortcut in the middle that we can take that's going to save us some time. It turns out that for binary classification, any linear classifier that I can write down can all be written as making decisions according to the sign of theta transpose x for some theta, okay? So basically what I'm saying is that logistic regression is not special. It just happens to be a particular model that I can assign a probabilistic decision rule, which then simplifies into this very general decision rule of looking at theta transpose x and looking at its sign. This is actually something that we talked about in lecture 1. If you go all the way back there, we drew this line that separates two classes, and then we characterize what that line actually is. It's always something that looks like theta transpose x, whether it's greater than or less than 0. And then if it's equal to 0, right, that line, or more generally that hyperplane in higher dimensional spaces, right, which corresponds to theta transpose x equals 0 for all of the x's where that is true, right, that's known as my separating hyperplane. Or more generally, it can be nonlinear if I have some nonlinear model, and then that's called my decision boundary, okay? So that's the point which basically separates between the two different classes, 0 and 1, and for a linear model, that's going to be a hyperplane, theta transpose x equals 0, all of the x's which satisfy that. So logistic regression is a probabilistic view of the binary classification problem, right? And this allowed us to use things like MLE, map estimation, figuring out how to do gradient descent on this particular problem, right? That's what it bought us, right? I defined the probabilistic model so that I could figure out what's the best way to try to optimize this model in order to get the best classifier. What we're going to do next week, right, is we're going to see a different geometric view of the same problem, of the linear classification problem, which leads to a model and an algorithm, very famous, very classic machine learning model and algorithm known as support vector machines, or SVMs. We're going to spend all of next week talking about SVMs because they're complicated, and it's a very deep topic with a lot of math, so do get ready for that. I was going to conclude today with a look at another very simple algorithm called perceptron, but we had technical difficulties at the beginning, so we're not going to get to that this time. We'll start with perceptron next week, and that'll actually tie us nicely into SVMs as well. Okay, so I'll stop there, and we have office hours now. Thank you.